Welcome to the first of many videos on motion for this course. In this video, we're going to introduce motion and talk about some important terminology, the definitions for position, displacement, and then we're going to talk about the difference between speed and velocity. We use those terms kind of interchangeably in everyday language, but in physics, they're two distinct concepts. One-dimensional motion is like kind of the simplest type of motion that you can study in physics, and it's the first step in understanding motion in more dimensions. So we're going to go into 2D motion, and you can even transfer that into your understanding of three-dimensional motion. So when we talk about motion, we're going to have to model objects as a simplified particle. So if you have a rigid system, you can use any point on the object as your particle because the system all moves together. So if we had a car, this is a rigid body, and you could call the front of the bumper as that's going to be our point on the object that we're going to model the motion of this point on the object, and that will represent the motion of the overall object. Okay, so that's what you can do for rigid bodies. But for things that are not rigid, you're still going to model it as a particle, but you're going to have to find the center of mass, or you're going to have to talk about your modeling the center of mass of the object. You can't just pick any old point and describe the motion at that point, because you can imagine, like a runner, if you chose a fingertip, the motion of the fingertip is not representative of the motion of the runner's body as a whole. Okay, motion is also relative to an observer. So different observers are going to see motion differently. So here we have this squirrel in a tree, and we have this guy riding his bike. Okay, for the guy on the bike, the headphones are not really moving with respect to him, but for the squirrel, those headphones are going to move through space as he rides by. Okay, so depending on the observer, so the squirrel would describe the headphones as moving to the left, or moving through space with some sort of velocity. And the biker, with respect to his body, the headphones are not moving; they're staying stationary. So you have to always establish a reference frame. You have to say, okay, where is my position 0? Where am I saying, okay, this is my spot that is always position 0, it's not moving, and you also have to identify the direction that's going to be the positive direction for your description of the motion. Without establishing a reference frame, your description of motion is meaningless because nobody knows where you're observing that motion from. So it's important, the first thing you do when you're going to look at the motion of an object, you have to identify what your frame of reference is, or we'd say establish a reference frame. Okay, so now we can have an actual definition of motion, talking about those two things. So we're going to define motion as a change in an object's position in a particular reference frame during a specified time interval. Okay, so it can be a short time interval, long time interval, but if it's changing its position in a reference frame over that time interval, it is in motion, or it's moving. It's important to remember that motion depends on the frame of reference. Okay, we usually think of the Earth as the surface of the Earth, the ground under our feet is not moving, but if you think about it from maybe in the International Space Station, then that doesn't seem like a good frame of reference to call this is our 0 point. That doesn't make sense because now that the surface of the Earth is rotating and you're going around Earth many times a day. So depending on the situation, you're going to change what you call your 0 point, your frame of reference, and your reference frame that you're saying is not in motion. Okay, let's define position. And yes, I know if I just said the word position, we don't really have to go through this, but there are a couple important things to note, so we're going to do it. So position is the location of a particle at a particular time in a convenient reference frame. So if we have these three particles, we can't begin to start talking about their motion unless we identify our reference frame. So okay, let's make a line right here. This is 1D motion. So all these points are on the same line, and we put a point that says, okay, this is our 0 point. So now that we've done that, we can talk about the position of our objects, or our particles, right? We've modeled our object A as a point A. So we can say, okay, well, object A is at a position of -0.5 meters. Okay, Oh yeah, and the arrow on my line there, that I use arrows to kind of indicate the positive direction. So with your reference frame, you always put the 0 point and then indicate which direction is positive. Okay, so point B, we could say, is now plus 2 meters. And C is at plus 3.5 meters. So once we get that reference frame, we can talk about the position of our objects. And position is a vector quantity. So you'll notice that I put the minus sign is important on position A, and the plus sign is important on position B and position C. It is the direction from the origin. Okay, so our positions have magnitude and direction, so they're actually a vector quantity. Next, we're going to look at something called displacement. And displacement is defined as our change in position of an object. So if there's a displacement, that means the object has changed position. And the delta is used across many different things to show a change. So delta kind of is our symbol for change. So if we have delta x, we can kind of see from our variable here that it means change in x. And we call that displacement. So our change in x, or our displacement, is going to equal our final position minus our initial position of that object. So again, displacement is a vector quantity. It has both a magnitude and a direction, because you're taking two positions that are both vector quantities, subtracting them from each other. You're going to get a displacement that has a sign, either a positive or negative sign, in one dimension that tells us that direction. Okay. It gets a little bit more complicated when we go into 2D with our direction, but with one dimension, it's very, very simple. We have either a positive or negative direction. This is different than distance traveled. Okay, so it seems similar, but we'll see in the next example that distance traveled is actually a different thing than displacement. It's a scalar quantity. It doesn't have a direction associated with it. So let's take a look at an example to kind of see that clearer. So displacement, if we're looking at the displacement of this bowling ball, let's say that we're at the bowling alley, and that at some initial time t naught, okay, we're at position x equals 0. And let's actually make that x equals 0 equal to 0 meters. So that will be we've established our reference frame, and let's call the right positive. Okay, so we're looking at two different snapshots of the same alley or same lane in the bowling alley. At an initial time and then at some later time down here. Okay, so at this initial time, we have a position of x equals 0 meters. At some later time, TF, we have a position of 18 meters of that bowling ball. We don't really care about what happened in between. We just know that, at one time point, we have a position of 0 meters, and at the next time point we have a position of 18 meters. So to calculate the displacement of that bowling ball, we just need to take the 18 minus 0, and we keep that sign. Okay, it has a displacement of positive 18 meters. This is different than distance traveled. The distance traveled describes the total length of the path traveled between the two positions. So let's watch that again. Let's say the bowling ball, when you roll it down the alley, roll or throw, I'm not sure what the terminology is. But that bowling ball usually takes a curved path if you're any good, if you can put the spin on the ball. So that curved path is not straight, and it's going to be longer than that displacement. So in this case, let's say it was 24 meters was the actual path length that the ball took. Okay. Oops. So the distance traveled, we would say, was 24 meters. Notice we don't put a positive sign because distance traveled is always going to be positive. And I keep going forward when I don't want to. So the path matters here. That path that it took mattered. And that the total path length, that's our distance traveled. Okay, it's important to distinguish between displacement and distance traveled because that is the difference kind of between average velocity and average speed. One is a vector quantity, one is not. One uses displacement, the other one uses distance. So average velocity is equal to the displacement divided by the time interval. So here is where we have our displacement, okay, our vector quantity divided by our time. So when we take our displacement divided by our time, we get a vector quantity. Okay? And our average velocity is not going to be the same quantity as average speed. Okay? You always have a direction associated with velocity. With speed, you don't. Speed is always going to be positive. Velocity has that extra piece of information that tells us which direction you're going. Okay, so taking a look at average velocity, and let's calculate the average velocity of that bowling ball. So our average velocity, we know our equation, delta x over delta t, or change in position over change in time. We calculate it always by taking the final position minus the initial position divided by the final time minus the initial time. So we are using the same example at time equals 0 seconds. We're at a position of 0 meters. At time equals 1.5 seconds, the bowling ball is now 18 meters to the right in our reference frame, which is in the positive direction. Okay, so our average velocity, we take 18 minus 0 over 1.5 minus 0, and we get positive 12 meters per second. So that's our average velocity. And if we look at speed, it's not going to be exactly the same thing, because now we're taking the path length, or the distance traveled, and dividing by that time. So the time is still the same. We have 0 seconds and 1.5 seconds. They're at the same spot there. Okay, but now what we care about is that total path, or that path length. Okay, the distance traveled is 24 meters. So let's go ahead and plug in our numbers. To get our average speed, we take 24 and we divide by the 1.5, and we get 16 meters per second. And in this case, we don't need to report that plus sign, because any speed that you report is always positive, because speed does not indicate the direction. It just is a scalar quantity. So with that, that's the conclusion of this first video in the kinematic videos. Thanks for watching.